Ander is still researching a digital media that is sufficiently strong and stable enough to be placed inside these dump sites to indicate to future generations the presence of nuclear materials buried deep underground. Perhaps they should look to the civilizations that sent us messages engraved in rock a very long time ago. These would be, for example, the hieroglyphs from ancient Egypt. Once again, the past is guiding us toward the future. We now have a mineral that is heat and acid resistant, that can withstand radio waves. It may not be indestructible, but in any case, it is far stronger than any stone obelisk. It is quartz. In Japan, engineers at the Hitachi laboratories, partnered with Kyoto University, have been working with quartz, trying to create the most stable digital storage medium ever created. They must, however, discover a way to overcome the extreme resistance of this rock crystal.
We began our research in 1996, when the Miura laboratory discovered that a laser could modify the structure of quartz. We then studied the possibility of using this technique for long-term data storage.
I am now going to record data on this sliver of quartz.
The data is recorded by a femtosecond laser. This laser emits pulses of around 1/1000th of a second. The pulse creates perfectly formed microscopic dots. A dot for 0 and a no dot for 1 in binary code. Dozens of dots can be recorded at once. The information is embedded in the layers, and it is therefore unaffected by dust or scratches. Another advantage of quartz, the transparency means that the information can be read by any microscope.
To conserve digital data for long periods, we cannot always rely on a reader to access information. If CD players were no longer manufactured, for example, it would become difficult to retrieve any data. With this technique, we can access the data using a traditional optical microscope. We could easily read the information even in a distant future.
What time frame? 100 years? 500 years? 1,000 years? 10,000 years? To test the strength of this medium, a slice of quartz in an oven heated to 1,000 degrees. 2 hours later, the slice and the embedded data are intact. It also withstands thermal shock when it is thrown into water at ambient temperature. An acid bath has no effect on it.
We determined that the life expectancy of the data we embedded on the strips of quartz is extremely long, from 300 million to several billion years. We could therefore store data reliably and safely for extremely long periods.
What is still an experimental procedure looks to be extremely promising. One major hurdle that remains is a limited storage capacity. For now, it is barely greater than that of Blu-ray technology. This would be sufficient to save the data of waste centers for a long time. Yet we are a long way from being able to handle the deluge of information produced by certain scientific tools. The CERN particle accelerator is a giant ring, 27 kilometers in circumference, buried 100 meters underground on the French-Swiss border. 2 particle beams are circulated at high speed inside this ring. Analyses of the collision of these beams, captured by ultra-sensitive detectors, have helped pierce the mysteries of matter and the origin of the universe.
We're here at the CMS detector, where the particles of the LHC collider come from both directions here, and they collide there in the middle and produce many collisions. You can compare this more or less with a digital camera, but in your digital camera, the sensor is about this size, whereas here you see it's a big volume, about 10 by 10 meters. And the further difference is that a camera typically takes 50 pictures per second, whereas here we take 40 million times per second a picture, which corresponds to producing 10,000 DVDs per second.
Given this quantity, information must be selected. Electronic filters only let through data that is considered pertinent.